Hi everyone, welcome to today's webinar. Today's topic is the automated workflow with JavaScript in RFEM 6. I am Doğukan Karataş and I'll be the presenter today. I'm the responsible engineer for developing web services and API technologies in Dlubal Software. And also I have two other attendees in today's webinar who is going to reply your questions, and maybe they can introduce themselves.
Thank you, Doğukan, for taking the word for the introduction. My name is Jaroslav Broz, and I'm leading the team which is responsible for development of API and also the scripting. And today I'll reply your questions in the question box.
Hello, my name is Thomas Günther, and I'm part of the support team with a focus on web service and API, C#, Python, and of course the older COM interface.
Thanks a lot. So I'm going to switch off my webcam and start sharing my screen. And I can start with a little presentation. Here, yes. So you can go in the control panel in this panel. There is a questions box, and you can ask your questions here in the ask questions, and our colleagues will reply your questions here. Okay, let me first introduce you the content of today's webinar. Today I will be explaining topics related to our JavaScript library and in-app scripting possibility. The first topic is in-app scripting, which is a direct interaction interface with the model. I'll explain what are the benefits and application areas of this technology and how you can access the source codes and the examples of it. The second topic is Dlubal Center and blocks, which is a standalone application for organizing projects, models, templates, and blocks. And Dlubal Center is the platform for accessing and editing all your blocks. After all the explanations, there will be a live coding session together. I'll write 2 scripts for 2 examples. The first one is a relatively easy one for creating moving loads in an existing model. And the second one is a trust generator, which I'm hoping that it will help you to understand how you can automate your workflow via scripting. Also, I will add some basic input user interfaces to these scripts. If you have no experience with coding or JavaScript, there is no need to concern. I will be explaining all the details, and also there is enough examples that you can make some small changes and meet your needs. Okay, let's start with in-app scripting. With the new generation of RFEM, now we are offering an in-app scripting console and script manager integrated in the user interface. With this feature, you can set or get information about all the objects via the console. This integrated console is responsive in JavaScript programming language. The advantage of in-app scripting is all the functions are developed as high-level functions. In other words, it's easy to read and write, and all the codes are stored in GitHub as a public repository. This means it's an open source project, and everyone can see the source code and everyone can contribute this project. What are the advantages of scripting? Well, firstly, you can parameterize a model easily. It's possible to create some variables in your script and create parametric models on top of these variables. I will show how to do it in our example. Also, you can automate some tasks. Let's say you're analyzing similar structures often. That means you can save your scripts and easily reuse them. Also, if you want to find out the properties of already defined objects, you can get all the information of an object via scripting, including geometry, loads, loadings, and add-on data. This scripting console based on the JavaScript 5 language. Since it's a fast and interpreted language, it's easy to write your code in JavaScript. and there are many resources online about it. You can write your scripts directly on the integrated console, or you can use any code editor to create your script. Then you can access your saved scripts via Script Manager. This manager connects the local file in the Dlubal folder named Scripts, which I will show you later in the live coding session. I already mentioned that we are storing high-level functions as an open source library. You can access this library under our GitHub account. And if you want to contribute or report a bug or request a feature, feel free to visit our GitHub account. There is a GitHub page under this repository for our functions. This you can use to find out the right arguments of the functions and the type of arguments. There are some examples in GitHub repo already, but you can find our default examples under your installation files also. I will place our example under that file. Plus, we will talk about Dlubal Center in the next slide. There you can find our intelligent blocks. This means you can find hundreds of JavaScript scripts embedded in the Dlubal Center for all types of structures. We believe you can find some inspiration in those blocks. The Dlubal Center is a standalone program to organize your projects, storing models, and using your template files. In Dlubal Center, you can also access extranet to view your customer data and purchased licenses. The most attractive feature of the program is the ability to store dynamic blocks. This means you can access your scripted blocks via Dlubal Center and insert them in the program easily. At this point, I should explain what are dynamic, or in other words, intelligent blocks. In RFEM 6 and Wstęp 9, beside the default blocks, one can create their own block for future reuse. There are 3 different types of blocks. For creating non-parameterized blocks, it's enough to save an existing model as a block. After that, you can insert this solid block in your models. Also, it's possible to add some parameters to change a property in your model in every insert. And the last one is dynamic or intelligent blocks. In this feature, you can link a JavaScript file to your block, and you can create multiple inputs and parameters with this code in your block. At this point, maybe I should mention that what we have added to our library since our last webinar. The most important point that newly added in the library is the function for starting the calculation. We have 2 options for this. First one is starting the calculation for all load cases and combinations. And the second one is starting the calculation for specific cases and combinations. I will use this function also in our example. Also, we added to erase and count existing objects. Erasing objects could be useful to eliminate identical objects, and also deactivating some settings if you want to reduce your calculation time. Counting and getting existing objects are useful if you're creating loops over your models. Okay, let's directly jump into the code, and we can start our examples directly. I'm going to use Visual Studio Code, and this is my example files. Here I have opened my RFEM 6, and if you go click this button here, you can see the script manager, and I have this folder here I have opened in Visual Studio Code. How you can find this? It's actually easy. It's under your installation files. You can see the scripts here. If you click here, this is the console that I can directly write some codes. For example, I can directly create a node here, node 1 at 0, 0, 0. I click enter here, I created it, as you can see. The first example I'm going to create is a simple moving load function. A moving load function that you cannot find naturally inside RFEM 6. So my point is to extend this functionality via scripting. For this, I'm going to create a simple beam now. Here, I'm going to select the material. and I'm going to select a still section here, maybe. Yeah. And I'm just going to create a simple beam here. Okay. Here I have a beam. Now what I want to do is I want to create multiple load cases with multiple loads. Then I can use them as a moving load. I'm going to go open my Visual Studio Code. Here under examples, I'm going to add a file called moving load.js. Now I have added it and I've saved it. If I go to RFEM6 now, you can see the script here directly. Okay, so I'd like to create a parametric model. That's why I have to create some variables inside the script now. I would like to create a load first. Let's say it's 30 kilonewtons at the beginning, and I'm going to create my second variable. I put steps, how many steps I want. Let's say it's 5. I'm just giving default values for the beginning, then I can modify them. And the last one is the member number, which indicates that which member I would like to assign this moving load. Let's give it 1, and I'm using semicolon for every line as a result of JavaScript language. Okay, then to create some member loads, first I need to create a load case. And to create a load case, first I would like to create a static analysis settings. I'm going to create a variable again. I'm going to call it analysis settings is equal to new static analysis settings. And I'm going to call this class, and this one is indicating the number of the static analysis settings. These functions that we created, these high-level functions, and maybe you don't know what is the arguments of these functions, then you can just go our GitHub account. Here you can see our repositories. We have a repository for Dlubal JavaScript library. Here you can see our source code, also our examples, also the documentation. For example, if you go to examples, here you can see all the examples here. For example, for creating a hole, a steel hole, you can check this hole.js. Also in this link in the right side, if you click on it, you're going to go to the Dlubal dev docs, and you can get started and take a look at the JavaScript commands at the left side, and the analysis settings is the first one. Okay, this is the modal analysis. I need the static analysis. Here, yes, I have my static analysis settings. So here you can see which parameters you have to use when you're creating a static analysis settings. For example, the first one is no. So in this table, you can see the type of the parameter is an integer, and here's the description. This is the unique ID of the static analysis settings. Also, the second one is analysis type. Here you can see which options you have to select as the analysis type, and it's so on and so on. There's lots of things you can choose, and you can also take a look how I can create a line, what I have to give. You can see the descriptions here. Okay, and now I'm going to go back to my code. I'm not going to give any other parameters because there is already some default values. I don't have to define all of them in every line. So a default static analysis settings is enough for me. Then I'm just going to skip the other arguments. Now for all the steps, I have to create a for loop, and I'm going to call an I is equals to 0, and I is smaller than the steps plus 1, and I'm going to create this loop, JavaScript loop like this. Yes. In this for loop, for every step, now I need a load case, so I'm going to create a load case variable, as new load case. And then I'm going to assign all the needed arguments inside this load case. So load case, I'm going to use the dot notation here. And this is a static analysis load case. And I'm going to create the brackets. And for example, now I'm going to give every I'm going to create the load cases with the IDs, but I don't know the IDs. So there is a function called the last ID. So I'm going to get the first 3 ID number. I can access all the load cases under load cases list, and I'm going to use the dot notation again, and I'm going to call last ID function. And for every loop, I'm going to add 1. Okay, it looks okay. Then the second one is the name of it. So let's call it moving load and plus I. So I can differentiate between the loads. This is moving load 1, 2, 3, 4, like this. And the number of the static analysis settings, and also which static analysis I'm going to select. It's 1. And which action category I would like to use. It's permanent G here. You can find all the strings inside the documentation. And lastly, there is a list for if I would like to use the self-weight or not. So I'm going to say false, 0, 0, 0 for every direction. So I don't want to use any of them. So, okay, I made a mistake here. This should be a semicolon. Yes, okay. Then I'm going to create the distance between the loads. Then I can create the member load. So distance, for distance, I'll create the variable, and it's 1 divided by steps multiplied with I. So for every steps, I'm going to get the distance for every load. Now I can create my member load. I'm going to call it member load is equal to new member load. Yeah. And then lastly, I can give all the attributes of this member load. So this is a force type member load. Open my brackets, this is the member load 1. And how can I get the load case? So I already defined the load case here. Load case dot get load case function, and I need to give the member no, so it's already an input, and the type of the load, so it's concentrated 1. Oops, sorry. Yeah. And a list for the magnitude and the distance. So the magnitude is load multiplied with 1000, because JavaScript language is always getting the loads in newtons. So I want to take an input from the user in kilonewtons. That's why I multiplied with 1000. And also I'm going to give the distance and a true argument for indicating the distance again. And the last thing is the orientation of the load, and it's an global Z. Global Z or user defined W true. This is the name of the global Z. You can find it also in the documentation. Yeah. So I created this one. Let's check if it's working or is there any issues with it. I'm going to double click it, yes. So as you can see, now I have created this moving loads here, and also the geometric, the linear static analysis settings. For every step, I have a different name, and this moving load is created via a script. So if I have a different structure, again, I can just go click this moving load, and this will work for every other type of structure. The good thing is For example, you would like to change these variables here. You don't want 30, but you want 20 kilonewtons. So you don't have to go to the script every time and change the variables. You can just create an XML file with the same name inside this directory. For example, I'm going to copy and paste it, and I'm going to rename it as moving load.xml. So how many variables I have? 3. So I'm going to delete them. I need just 3 of them. Let me close this and split my screen. Yes, the argument name is, for example, load. Here, load. Second argument name is steps. Third one is member. No, I can give some default values. I'm going to give the same values here in the default value, 5, and this default value is 1. And also I can change the label name. So this one is the load in kilonewtons. And this one is the steps. And this one is the member node. Okay. I just saved it in the same directory here. And if I go to RFEM6, let's delete all the things we created from the last script to not to overwrite something again. Delete them all. Okay. Now, if I double click it, you can see there's a script visit. Now you can change these parameters according to that. And here in the script, it can override all the values. But something we should arrange here, because every time you run this 3 of them will be overwritten by the script itself, so XML is useless. Maybe I can just add a if condition here. If load is equal to undefined, then use these default values. If it's not undefined, if it's coming from the XML, you can use the values from the XML. Okay, I'm going to go to RFEM6 again. Again, I'm going to delete this loads to avoid the double writing for the loads. So when I double click it, okay, for example, now I want 20 kilonewtons in 8 steps for the member. I have just 1 member, so I'm not going to change it. Member no 1. Run. Now, as you can see, I have 20, and also I have 8 steps for my moving load. That's the way how you can create some easy and basic user inputs for your scripts, and you can make an automatic workflow for your projects. Okay, this one is a relatively easy one. So let's go for another example, which is a little bit more complex. So I'm going to delete everything inside this file. Okay, we don't need this one. And let's create a new file. And this is going to be a trust generator. So I'm going to call it a trust generator.js. I'm going to create a parametric solution for generating 2D trusses inside RFEM6. And as always, I'm going to create some variables. Let's call it n. This is the number of base, 10 for default. And second variable was h, its height, and 2 meters. L stands for length, call it 1 meter, and the distributed load. Here, 1 kilonewton per meter. Okay. That's the for variable. I'm going to make parametric for this example. Of course, you can create more parametric models, not like for. You can create some materials sections, blah blah blah. It's up to your imagination. But for this example, I'm going to create materials and sections manually. So The first material is also, I'm just going to create one. The material is a steel material. I'm going to call it undefined, and S235 steel material. Why I gave undefined here? I can give also 1 or 2, but for the future reuse, I don't know how many materials is defined inside RFEM6. If I give undefined, it will go and find first 3 ID number. For example, if you have 3 materials, now this material will be the 4th one with this undefined function. And I'm going to create 2 sections. Let's go section 1 is equals to section undefined. I'm going to select IP 200 for the top and bottom chords. And I need to specify the material. So I already defined the material here. I called this one, as you can see. And the second one, I'm just going to copy and paste this line, the section 2. I'm going to use it for the diagonals, so I want to use a circular hollow section. So CHS 60.3, and the thickness is, let's select 3 millimeters. So it's my section for the diagonals. Okay, now I will create the nodes first. Let's create a comment, so you can create some comments like this. So it will be more explanation inside the codes. I prefer to create all the nodes from scratch, and then I can push all the variables inside this existing nodes. For example, now I need a for loop also for variable I is equal to 1, because first number of the nodes should be 1, until I is smaller than 2 multiplied with n plus 1, because when you're creating 10 base, you need simply 20 nodes, and just plus I for the loop. Okay. Now I can just call my node function with I. When I run this, let's try every step inside RFEM6. You see my trust generator file is here. I double click it. As you can see now, I have 20 nodes created here. Okay, and also yeah, we created the material, and these 2 sections, they are created with these lines here. Also, I have 20 nodes now. Okay, let's push the real coordinates of the top chord first. I'm going to add a comment again, top chord nodes, and again a for loop I equals to 2, because I want the first node in 0, 0, 0 location. That's why I'm not going to change anything. So I'm going to begin with the node 2 until n plus 1, because it's just a top chord, and plus I. Okay. Here now I have to create my geometric equation for x coordinates. So x is equal to L, I mean the length, multiplied with e minus 1. This is my x coordinates for all the nodes. So now I can push this x coordinates to the nodes. So I can access these nodes via the nodes list and I. So it's 2, 3, 4, 5, and push them to the coordinates. Now I have to use the $sign as a JavaScript library syntax, and V. Now I can push X, and Y is 0, Z is 0. Now I pushed all the X's to the top chord nodes. Let's try it again in the RFEM6, delete them all. It's empty. Now run this. As you can see, I have my top chord nodes now here. But still, I have, as you can see, 20 nodes, and half of them is 0 because I'm going to push new coordinates for the bottom chord for them now. Let's create them. Button code nodes. Again, a for loop. EI equals to n+2, because the last node here, as you can see, it's 10. So I have to start with n+2, and it should be until the end of it. So same loop like here. It's 2 multiplied with n plus 1 and plus I. Again, for the bottom code, I need a geometrical equation of the x coordinates. So I want to create the bottom code nodes in the middle of top code nodes, like here and here. So that's why I'm going to call it L divided by 2. And also I need to add the x coordinate. I have to shift this nodes. And this is I minus n and minus 2, because I don't want to have too much bottom code nodes in here. So this is multiplied with L. This is geometric equation for x. Again, this is semicolon here. Okay, now I can push them also. Nodes I that coordinates is equals to $v and x 0, and now this time I need the age, so for the height. Let's write, delete everything, run trust generator. Yes, now I have this bottom codes and the top code nodes, because I want geometry like this. Now, as you can see, I have 2 nodes here, 1 and 11. This is a consequence of using loops. Now I'm going to fix it immediately when I show this. Yeah, this will be the geometry of my truss. Okay, I'm going to delete every one of them. Now, as you saw, I have 2 identical nodes because of the loops, so I need to delete one of them. And I'm going to call the nodes list and use the function erase. And I have to use, for example, I have 10 number of base. Now my duplicated node is 11. It's always n+1. Okay, I'm going to delete always the node n+1. Now, since I have the nodes, now I can create my members. Let's start with the top code. And creating my for loop again for I equals to 1. My first member is the member 1 until n and plus I. I'm going to call my member class from high-level functions library. Member node is I, and I want to begin with the node 1 to 2, for example, and 2 to 3. That's why I and I+1. Okay, and then I can push the section to this created members. I'm going to access them via members list. I section start is the right comment, and I can select sections 1, which is the IPE section I created here. Let's try again. Double click. Yes, now I have my top code here created with IP200. Now let's create the bottom code. It's a little bit more complex to create bottom code members, because now I have already created 9 members, so I need to duplicate this number. I'm going to call something called j equals to n. I'm going to use this j in my for loop. So var variable I is equal to 1 again, and it's going to be until n minus 1 and plus plus I. And now I'm going to call my member class again, but this time it's J. Here I created from n. And then I'm going to begin with n plus I plus 1 I need. So because it's the 12th node here. Yeah, as you can see here, it's 12. I'm going to begin with 1 to 12, then 2. And until n plus 1 plus no, sorry, this is the bottom code, so I'm going to go to 12, 13, 14. So I just need to add 2 here. Yeah, that's easier. And I'm going to push the members for these lines in section start and section, and the first one again, this is the IP section. Okay, looks okay. Let's start. But yeah, I just created this J here, so I need to add 1 in every loop to this J to create different member numbers. Let's try. Delete everything. Double click. Yes, I have the bottom code now. Now it's time to create the diagonals. Comment again, diagonals, and again a for loop, begin with 1, and I is smaller than n, and plus plus I. Now, first I would like to create my members, then I can change the type, and also I can change the section, because these are the trust members. I don't want to create these diagonals as beams. For example, now the type of this member is beam, but this diagonals should be trust members. Now I'm going to show you how we can change it. First, I want to create a member variable is equals to member class beginning with J again until I n plus I plus 1 is the right equation for diagonals, I believe. And then I can access this members. J is equal, sorry, its section start is equals to sections 2 is the circle hollow section. And then I can change the member type, members J type. This is working with an integer, so if you can go to this member type, as you can see, beam is the member type 1, rigid is 2, rib is 3, and truss is 4. So I want to use the truss member, so member type is simply equals to 4. Okay, let's run this and see if our geometric equation is true or not. It looks like it isn't, because I'm now overwriting some values here. I'm going to go back to my script and trying to find out where I did the mistake. Member J here. E is smaller than n, it's true, yes. Yes, because I'm not created any. I didn't add any number to J, so it's always the same value. That's why. Okay, now let's try it again. Yes, just this direction. It's created, and it's circular hollow section, and it's the member type truss here. Okay. Now I want to create the other diagonals also. I don't have to create any other for loop. I can just use this one, and let's create a new member here, member j plus 1, because if it's, for example, if it's member 18, then I have to create 19. Then start with e plus 1 to n plus I plus 1. Okay, this should be the right way. And here I can access my list to member j plus 1. Section start is equals to sections 2. And members j plus 1 type is also 4, so it's type truss. Let's try it again, delete all. Oops. Just generator, double click it. Yes, I have my geometry here now. Okay, great. Now I created the geometry, it's done. Now we are done with the for loops. And I just want to apply some loads and start the calculation with JavaScript. That's why first I need to create some boundary conditions with nodal supports. So I want to create a nodal support 1. This is one type, is equal to a new nodal support. Let's call it nodal support 1. And since I want to calculate it in 2D, I'm going to assign a hinged support here. So if I call this hinged function, now nodal support 1 is a hinged one, but also I want to check the box for rotation on the X, since we are working in 3D, but I want to calculate in 2D. So you can say nodal support 1, rotation X should be true. So that's how you can, for example, now I'm going to delete all and show you my nodal support in types for nodes here. Normally a hinged here, when you call the hinge function, it's like you're clicking this. So this one is the hinged. If I go and say reduce the rotational X here, so I need to check this box here. Here, this line is doing this. Okay. Now I created this one, and I'm going to assign this nodal support to some nodes. So node 1, the first node, support is equal to nodal supports 1. And also I'm going to copy and paste it. Nodes n, the last node, should also have this nodal support. Okay, let's try it. Delete all, like always. Double click. Yes, now I have my supports here. But the bottom code is free now. So if I run the calculation, there will be a singularity in stiffness metrics. So that's why I would like to create some nodal supports also here and here in X direction. Let's call it nodal support 2 is equal to nodal support 2. Yeah, and nodal support 2 should be restricted in translation Y. Translational Y, it's true, and also rotation X. Support is rotation X is true. Okay, let's see if it's working properly. Translational Y, undefined is undefined. I think I misspelled it. Why I don't need translational here. Okay. It's not a function. We'll see. No, that's just a function. It's not an attribute of the support, so it should be like this. Okay, translation y, true. Like the hinge there, it's a function. Okay, nodal support view, also rotation x is true. Let's try now. Yes, here I created nodal support 2, translational y and rotational x, but I didn't assign the nodes yet, so it should be nodes list, and I want them here and here. As you can see, I have 10 number of base, and this node number is 12, and also this node number is 20. So it's n plus 2, and it's 2 times n, obviously. So n plus 2 is dot support with dot notation is equal to nodal support 2. Copy and paste, and let's assign it to 2n. Try it again. So it's somehow debugging inside RFEM6. Yes, now I have my nodal supports here. So now it's stable. I can create a calculation. Okay. Sorry. So as you remember, we created something called loads. So I need a distributed load on top code. So now I'm going to create it. Assign load. But first, what I need is a static analysis settings, as always. Var, its variable. Let's call it static analysis settings geometrically linear is equals to new static analysis settings. And now I can use this variable name to assign some new functions like geometrically linear is a function for creating geometrically linear static analysis settings. Yes, and let's call it assign static analysis settings. This is better. Comment. Let's now create load case, and I'm going to call it load case is equals to new load case. So this is my variable name here, and I can use it like load case dot static analysis settings. Now I'm going to open my brackets. This is the load case 1. The name of it, let's call it that. And the static analysis number is this one. So I can just copy and paste and tell get no function. Oops, it's just a comma. Yeah. And the name of the action category. So I'm going to select action category permanent G. As I told you before, it's these action categories can be found under our documentation. Let's create a list to activate or deactivate the self-weight. Let's just activate it with true. Let's it should be on Z, so it's 001. Yes, I have created my load case. Now maybe I need a design situation, so set design situation. I'm going to create a variable called design situation is equals to new design situation. That's 1. Yeah. And now I can access them via my design situations list 1. Now I'm going to assign a type of design situation. Okay, design situation type is equals to 6194. Okay, what is this number? Let me explain what is this here. I'm going to delete all and run my script again. Load case statica undefined is not a function. Let me check here. We made a mistake. No, this is just static analysis, not settings. Here. Let's try again. Yes, it's created. Now, I was going to explain what is this design situation type and the number. Okay, let's go to load cases here. That, as you can see here, I have some design situations. So, for Euro code, you have this permanent, transient, characteristic, frequent, seismic, and so on. So here you can see the combination rules for this design situation. I have selected the SLS frequent, but how do I know this number? This number stands for this frequent. In order to get familiar with this, you can open your console. You can click this I button here for the information. Okay, here I can go to this design situations. Oops, not like this. And I have to find the design situation type here. Okay, now as you can see here, I have all the names, all the values, and you can see the number of these values. There is an integer for all the design situation type, and SLS frequent is 6194 here, and I gave the number of the design situation. So I created this SLS here as a serviceability configuration for my design situation. Okay, let's delete them all. I have my design situation also, and now I can create a load combination. Create load combination. Yes, and let's call it load combination is equals a new load combination. This is load combination 1, and the second argument is the static analysis setting. So I'm going to use this one. Get no, and the other one is the design situation, and I'm just going to copy and paste get no, and there's a list of load cases and the factors of load cases. So the first one is load case.get no, and let's do it 1.2 for now. Now I have created my load combination. Now it's time to create a uniform member load for the top code. Okay. Uniform member load here. So I'm going to create a variable called member load is equal to a new member load class. It's an instance of this class, and I'm going to create a for loop for the top code members, because it's not just one member. There is plenty of members in my top code, so I need a for loop here. Variable I is equals to 1 until n, and plus I here. Okay, curly brackets. And now I can push some variables into this member load instance. It's called force, and the member load number is I, and load case is load case dot get load case function I'm using, and yeah, this number is can be also I, and also the type of the member load is uniform, and the magnitude is load multiplied with 1000, as I mentioned in the moving load example that I have to change it to kilonewton. That's why. Okay, now I've created it. Let's check. Close this console for now. Just generator. Yes, as you can see, here is my member load. Let's check the load case, permanent, geometrically linear, design situation is created, and the load combination. Here, I should have one, not like two. Maybe we can check this. Why we have two of them. Let's comment it out and check it again. I'm going to delete them all. Okay, go to load combinations. Now it's not created at all. Okay, load combination here. So I can use my Dlubal dev docs, right? Here, JavaScript comments. Here, loading. Design situation, type, params, it's true. Load case. Okay. Looks true. And load combination. Number, design situation number, design situation number, and combination items. Okay. Here we made a mistake. Apparently, you just call the load case. Here. Design situation number is 1. And load combination items, right? Load case get no as a function, yeah, and 1.2. Let's see if it works like this. No, at least one load case must be specified. Load case no factor. Yeah, load case no factor. Okay. Now here is the analysis settings. We forgot this one. Okay. Analysis settings is also 1. I'm just going to add a 1 here, and we'll see what happens. Okay. Go to load combinations. Here. Again, that and that. Actually, I just created 1. Not like 2. I create like this. Let's start this. Trust generator here. Again, 1 that. Yeah. Maybe there should be a small bug inside the slot combination, or I just couldn't solve the issue, but let's not stuck with it. We can solve it. Also, I can send you an email after our webinar when we solve this issue. Okay. I'm just going to show you how you can activate the still design and then start the calculation. Okay. Here I created the member load. Now I'm going to activate the still design, and I'm going to call still design dot set active and true. Yeah. Then I can just call my function to start the calculation. Calculate all. Okay. I'm going to go to RFEM 6 again, delete everything, double click, And as you can see now, generating mesh and the calculation has started. It's done. Now I have the results here. If I can go here, you can see still design here, static analysis here, results by nodes. You can see the results immediately here, like this. Okay, and also I would like to make this parametric, so I want to add an XML file for trust generator 2. I'm going to copy and paste this and name it as trust generator.xml. Okay, now I'm going to split it, and I have NHL load here. Yes, so let's call it NHL and copy and paste it. Load default value 10 2 1 1. Okay, the first one is number of base. The second one is height in meters. The third one is length in meters. And this is the member load in kilonewton per meter. Yes. Again, I need to add a small if condition to not to overwrite the values. If I can select one of them, it's no issue really. If, for example, n is undefined, then use these values here. Okay. Now I'm going to go to RFEM 6, delete everything, double click my trust generator, and here is the script wizard. Let's try it. Yes, it's working fine, and here is my results. For example, just change some values. I need 16 base with 3 meters height, 4 meters length, and 2 kilonewton per meter. This is the good part of making this parametric scripts. Now I have my trust generator that I can use any type of structure like this. Okay, this is the end of my examples, and if you have some questions, you can send your questions via dlubal.com, or you can take a look at our free online services, also my JSON tool and facts and knowledge base, and you can get our YouTube channel, and you can get a web shop with prices. Also, for the further details, just visit our website dlubal.com, and you can also send some emails to info@dlubal.com for further questions. I hope you enjoyed it, and thanks for joining, and I wish you a nice day. Bye bye.